We have another smaller section to do for us today, mostly because we've already done a bunch of the work needed for this section in a previous section when we were talking about inequalities with quadratics. So for both polynomial and rational functions, our generic inequalities are going to look like the function, and then we'll have some inequality compared with 0. And that's for the same reasons we just had a simple situation to consider with the quadratic functions, is because when you have stuff on opposite sides, you can always move everything over to one side and combine it. So we'll start with the polynomials. Here's a nice little example for us to practice with. We have x cubed plus x squared less than or equal to 4x plus 4. And we're going to take the same process that we did with the quadratic inequalities. We're going to move everything over to the same side. So I'm going to move everything over to the left. So we're going to be looking at x cubed plus x squared minus 4x minus 4. And we keep our inequality here. So we have a polynomial less than or equal to 0. And what we want to do every single time is find the x-intercepts, just like with the quadratic ones. It's basically what we're doing is we're pretending the inequality is going to be an equal to 0, so we're going to be looking for the zeros of the polynomial function. When we had quadratics, usually we can factor, or at the very least use the quadratic formula to try to find the x-intercepts. But if here I have a cubic, and in fact the higher degree polynomials can be much harder, so the next section, 4.5, is actually going to help with the higher degree polynomials with these types of problems. Fortunately, this is one that we can do by factor by grouping. So out of the first pair, let's mark them here. Out of the first pair, I can take out x squared, leaving me with x plus 1. Out of the second pair, I can take out a minus 4, and that'll leave me with an x plus 1. So I have an initially factored form, x squared minus 4 times x plus 1. And I can keep going there because that's the difference of squares. So I've got x plus 2, x minus 2, and x plus 1. And we are looking for when it is less than or equal to 0 or below 0 if I were to graph it. So my x-intercepts are x equal to minus 2, x equal to 2, and x equal to minus 1. Now what I really want to do for most of these is draw out a nice little number line with my x-intercepts. Looking at minus 1, minus 2, and 2. So my roots were at minus 2, minus 1, and positive 2. So on our number line, what we want to do is we want to look around each of the x-intercepts. So I want to pick a number between these two somewhere. I'll pick $0 because that's between negative 1 and 2. And then I'll choose numbers on the outside. Since I have 3 x-intercepts, I'm going to need 4 test points. And what we'll do is we will plug those into our polynomial function. I think it'll be easier if we plug it into the factored form. So let's start with -3, f of -3. That'll be -3 plus 2 is -1 times -5 times -2 works out to a -10. So what I want to see is that I got a negative number there. Now I'm going to try f of -3 over 2. That's going to be that point that's right halfway in between -1 and -2. If I add 2 to that, I will get 1/2. If I subtract 2 from that, I will get -7/2. And if I add 1 to that, I will get -1/2. And if I multiply all these together, I get a positive number, +7/8. But I just really care that it's a positive number. What's next? F of 0 that I picked there. If I plug in 0, I'll get 2 times -2 times 1, which is -4, which is a negative number. And lastly, I need to plug in 3. That'll give me 5 times 1 times 4, which is 20, which is positive again. So what I see, without actually drawing a graph or anything, I can tell that the graph of my polynomial is going to alternate from negative to positive to negative to positive. As far as a solution to the inequality, well, I was looking for less than or equal to 0, or whatever is below 0. So I'm looking at the negative parts. So my solution is going to be -infinity up until I get to -2, because that's my first x-intercept. And I'm going to block that off because I had less than or equal to. I skip over this next interval because it's positive there. And I start on the next interval, which is going from -1 up to 2. And I can include that one. And then it's never a negative value again. So just like we had for the quadratic functions, my polynomials are continuous, which means if I have positive numbers for a test point in an interval between x-intercepts, then every number in between those x-intercepts will be positive. And similarly for negative values. Now I can do all of this same stuff for rational functions. Let's try one. We've got x squared minus 8x plus 12 all over x squared minus 16. And we want to find out when this is greater than 0. Now this actually works exactly the same way that it does for polynomials. The first thing I ever want to do with rational functions or with polynomials is to factor them. So let's see. I can do x minus 2 and x minus 6. And I'll have x plus 4 times x minus 4 on the denominator. I'm looking for when that is greater than 0. Now what I'm still doing is I'm still finding x-intercepts because I'm going to test points in between the x-intercepts, but I'm also going to be watching out for where I have vertical asymptotes, because my graph can change from positive to negative across an asymptote. And that's exactly what I'm after here. I'm looking for when the graph is specifically above 0. So let's list these. We've got x-intercepts From the top, they are x equal to 2 and 6. And I have vertical asymptotes at x equal to -4 and 4. So these here are all of my points of interest. If I was taking a calculus class, I might call them critical points, although that's a slightly different situation. I'm still going to make a number line for all of my points of interest. So let's see, I go from -4, nope, I'll have to go farther than that. -5, -4, -3, we'll have to make this longer. And longer still. That's a big number line. Okay, let's see. Our points are at 2. My x-intercepts are at 2 and at 6. My vertical asymptotes were at 4 and -4. Now, it doesn't matter a whole lot that I differentiate between these two. All that's important is that at these points, -4, 2, 4, and 6, my graph can change from positive values to negative values. So let's see what points I'm testing. I will try -5. 0 is always easy. And then I need another one for 3 here. I'll do 5 and 7. I have 4 points of interest, so I should have 5 test points. Now let's see what we get as a result. F of -5 will be, let's see, up here, -7, -11, all over -1 times -9. This comes out to, that's a lot of negatives, but it'll be a positive 77 over 9. But again, I only care about really keeping track of the negative signs. I just want to know if this is a positive number or a negative number. What number it is not important. So I got a positive number at -5. Let's find out what we get at 0. F of 0 is -2 times -6 divided by 4 times 4, -4. This is going to work out to be a negative number because 2 of my negatives will pair up and cancel, and I'll still be left with a negative. But specifically, what do I get here? -12 over 16. I can simplify that, but again, I just care that it's negative. What's next? 3. F of 3 will give me 3 minus 2 is 1 times -3 divided by 3 plus 4 is 7 times -1. So you can see I'm just looking at these by the factors of the numerator and denominator. This works out to, it's a positive number. It'll be 3 over 7, whatever, positive. Plug in 5. We'll get 3 times -1 over 9 times 1. That's a negative number. And lastly, 7. F of 7 will give me 5 times 1 over 11 times 3, which is positive. So my graph starts off positive and it alternates between negative and positive all the way through. So here I was looking for when it is greater than 0. So I'm looking for when my graph is positive. So my solution set will start here from negative infinity, and we go up to 4. That's our first vertical asymptote. So if I had a let greater than or equal to symbol here, I would still not include 4 because 4 is a vertical asymptote, so I can't ever include that no matter what kind of inequality I have. Which is why it might be helpful at this step when you're drawing your number line that you do something to differentiate between the x-intercepts and the vertical asymptotes. Let's see, our next chunk for greater than 0 was between 2 and 4. So I get to, I still don't get to include it. If I had the greater than or equal to, I would do a square bracket for 2, but I'm not including any endpoints for this problem. 2 to 4. And then we skip over the next one because it was negative. And then finally, we have 7 to infinity. We'll do one more, just because when we have polynomials, it's easy to go from one that is split across the inequality to one that is properly set up with a function on one side and 0 on the other. If you're giving a rational equation that's set up properly, well, that's good. But we won't always have everything going our way. Let's take a look at this one. 2x minus 6 over 1 minus x less than 2. Now there's a good way and a less good way to do this. The good way is to simply move the 2 to the opposite side. So I've got minus 2 less than 0. And then here I would find a common denominator. Less good would be to multiply both sides by 1 minus x. Turning it into a polynomial problem. The problem with doing it this way is once I turn it into strictly a polynomial problem, I will lose out on the information that I had down here. I'm supposed to have a vertical asymptote at x equal to 1. That's not going to happen if I multiply both sides by 1 minus x. So it's safer to move everything to one side and then find common denominators than it is to just simply try to simplify the problem. So let's make a note here. This loses vertical asymptote from 1 minus x. So it still looks like it's a factor up here, but it won't necessarily become a factor of the polynomial, and so I would have literally lost information about my original problem. So let's continue with the good way. Let's see, I've got 2x minus 6 over 1 minus x, and if I find a common denominator, that'll be 2 times 1 minus x over 1 minus x less than 0, and we will combine these. Let's see, I'll do two things at once here. 2x minus 6, I'll distribute the minus 2 through there, so I've got minus 2 and a plus 2x, and this is all over the common denominator of 1 minus x. We should be pretty good to go now. I've got 2x plus 2x, so I've got 4x, minus 6, minus 2, minus 8, all over 1 minus x, less than 0. So going back to the less good way, if I simplify what I have up here that's less good, all I'm going to get is this rational equation part down here but I won't have a denominator at all. It'll just be 4x minus 8. It'll be a simple polynomial. And it's going to be missing my vertical asymptote. So basically it's just a completely different problem. So what do I have from my problem? 4x minus 8 gives me an x-intercept of 2. And we have a vertical asymptote of x equal to 1. So we can make a number line pretty easily with those. We'll start here. We've got negative 1, 0, 1, 2, and 3. Our points of interest were x equal to 2 as an x-intercept and x equal to 1 as an asymptote. So my test points are going to be 0, 1/2, and 3. So let's try this. F of minus 1, nope, what am I doing? My test point is 0. F of 0, I'm using my work down here. This will be 4 times 0 minus 8 over 1 minus 0, which is just minus 8. We get a negative number. Our next point is 3/2. So we've got f of 3/2. Let's see if I plug that in. That'll be 6 minus 8 all over 1 minus 3/2. Looks like it works out to minus 2 over minus 1/2. Those cancel to become positive. It'll be positive 4, it looks like, but it's positive. That's all we care about. And lastly, f of 3 will give us 12 minus 8 on top and 1 minus 3 on bottom, which is 12 minus 8. 4 over minus 2, which is negative. So I'm looking for when this guy is less than 0, giving me the solution set. Let's see, I want less than 0, so I want negative parts from here. It's minus infinity up to 1. Can't include it because it's an asymptote, and I can go from 2 to infinity because it's going to be positive forever after that. And just as a note, if I had included an inequality here for 0, all that would change is when I get to my answer, I would switch to a square bracket for the 2. Not for the 1, because that one comes with an asymptote, so I can never include that. Our next section is going to be pretty heavy on factoring, because it's about finding all of the zeros of a polynomial, but it goes right along with the section after that, which is 4.6, which is complex zeros. So hopefully I should have another video up in addition to those, just with some information about complex numbers before we have to deal with those.